you know where it originates from?
What's that?
The word Bodhi?
It's a guy's last name, actually. Bodhi was, the guy's name was Frederick Bodhi. I guess he was originally from Germany, and he worked at Bell Labs over in California, and did a bunch of cool stuff, including came up with this quick and dirty way of looking and visualizing these things. So, like most things recently, it's named in honor of some guy who invented it. So I suppose there's a possibility, and I'd have to go back and check, but there's a possibility that Norton and Bodhi were working at the same time at Bell Labs. Possibility. And actually, I don't think, I would have to talk with Mr. Secor about it, but he also worked at Bell Labs, so he might have, it seems unlikely, he seems to not be that old to have worked with like Norton and Bodhi, because Bodhi did this work, I was reading, I think in the 1930s, and so I think that predates all of our faculty, so. I'm trying to remember the numbers. I think Bodhi passed away in like 1982. So, all right. So let's see. This is going to be day number last of official recorded classroom time. Tomorrow, what we'll do is we'll do a quick quiz on probably Bodhi plots, since we're going to take a little bit of time to finish that up today. And then after that, if you want to stay and you have questions on any of the material over the entire course of the semester, feel free to ask that. Otherwise, I will put up on Blackboard, I'll put up a final exam review slide sets, the things that I expect for you to be able to know. But it kind of boils down to anything we've covered in class has the potential of showing up on the final exam. Anything from basic DC analysis, Thevenin equivalence, Norton equivalence, superposition, linearity, first order transients, second order transients, AC analysis in all of its varied forms, doing the power stuff, doing the simple Bodhi plot, doing what we'll look at a little bit later today in terms of the resonant circuit stuff. So pretty much anything could be on there. The structure of the exam is going to be very similar to what I mentioned yesterday, and that's there will be 5 required problems, which is material that we've covered since the last exam. And then there will be, I think it's written so that there's 5 optional questions, and you'll choose 3 of those. So you can, if you don't like Thevenin analysis, then you don't have to do a Thevenin analysis problem. It's kind of up to you on which ones you want to do. The exam is almost done. Yeah?
Can you give us a formula sheet?
Yeah, I will post it will be just more, it will be more complete than the one that you got for the last exam, because it'll have things like the average power formula on it and stuff like that. I will, if that doesn't go up shortly after class, please remind me, and I will post what the formula sheet looks like. Yeah?
Will the review slides be up today or tomorrow?
I'll try to get those up today after the final exam is completed. It's almost, I have to go, and I realized as I was trying to put it together that I have one more slide or one more circuit image to draw and scan and get imported into the editor there. So, but otherwise, the circuits are drawn. I just have to modify the questions to make sure that they reflect what I'm looking for in the version of the circuit that is in this exam. So. Yeah, it should be, we'll try to get all of that stuff ready for you. I'll grade now that the online students are done, I will get your homework's graded that you turned in yesterday. I'll get your quizzes graded that you did. Let's see, the homework was turned in on Monday. The quizzes that you did yesterday, I'll get those graded. And so those will be ready to hand back tomorrow. So you can pick those up as well. And then what I'll do for the quiz that we do tomorrow is I'll get a solution to that posted online promptly. So the homework assignment that I put up on Monday, the 5 questions from this chapter 12 material, I think I even put the due date as like 4 o'clock on Friday. So yeah.
Put up the solutions for that one too, so we can check over.
Yeah, I'll do that. Put the solutions right up. So, all right. Are there any specific questions on anything? Okay. So like I said, I spent actually most of the day yesterday after I got done with, once I got back to my office, took care of some, miscellaneous things. Spent most of the day looking at Bode plots and trying to come up with a really solid understanding of why some of the things that we did yesterday didn't necessarily match up with what was in the solutions from the textbook and how these things were working. And I noticed 2 things. Number one, I neglected to give you one of the rules, which it wasn't in my notes. I don't know why, but there's a a special set of rules for dealing with poles and zeros that are at the origin that don't have, we had talked about this, like j omega plus 10 and j omega plus whatever, and those give you all of those break frequencies. And if you just have that naked j omega term, so its break frequency should be, somewhere around 0, right? Well, the behavior of that is slightly different, and we'll talk about that. The second thing is that, well, perhaps we'll crank that up to 3 things. The second thing is that textbooks are really odd in their coverage of this. I think I went down to the faculty reference room in our building, and I looked at, I think, 6 different textbooks to try to find some coherent stuff about Bode plots, and it was really hard to find. And one of the hardest things to find is, where does the Bode plot start? When you get over towards that 0 point, the origin, where does it hit the x-axis? Where does it hit the y-axis? That is something that nobody has a really good answer for, and it seems like the official answer as far as it goes is it kind of starts wherever you want it to. So and that's in terms of where on the x-axis you start drawing your Bode plot, because you can just start drawing it, wherever. It's cool. If you want to start drawing it as far to the left as possible and getting towards 0 radians per second, there are some ways of solving for that are not totally evil. So, but I did find at least one really good reference, and so we'll step through these things in a way of review as well as completing what we had been talking about. So, the things that we had talked about that are very straightforward are, let's see, if you have a constant k term, the Bode magnitude plot of that is just going to be a straight line of the value 20 log base 10 of k. That's pretty straightforward, nothing weird there, and that's not different from what I had mentioned before. For what it's worth, the phase plot is a flat line at 0 degrees, but we're primarily concerned about magnitude plots, so I'm not going to worry about the phase plots too much. If you have a term that is at the origin, and we're going to generalize this as much as possible, and I'm going to say that you have, regardless of what power that's raised to, you can raise that origin term, whether this is going to be a 0 at the origin, any degree, n, and if it's multiplied by some constant k0, then what you're going to have is a linearly increasing term that crosses, so this is omega on both of these axes. It is going to cross it's going to be linearly increasing at 20 dB per decade, and it's going to cross the origin at exactly 1 over k0 to the 1 over nth power. And so for a simple, if n happens to be 1, for example, and k0 happens to be 1, then when you plug that in over here, you have 1 over 1 to the 1 over 1th power. And so for a really simple, if you have a j omega term of degree 1, and there is no k0 term specifically, then it's going to be a 20 dB per decade linearly increasing function that crosses the crosses the x-axis at 1. But this is the most general form of this equation, or general form of the situation. So that if you have some constant k0 multiplying your 0 at the origin to some power n, this is actually n times 20 dB per decade. That's important. That means that if you have a squared term in that numerator, that's going to increase at 40 dB per decade. If you have a cubed term up there, it's going to increase at 60 dB per decade. Okay? Now if you have a pole, and again, of the generic form of k0 over j omega to some degree n, some power n, what you're going to have is the opposite situation where it's going to decrease at 20 times n, negative 20 dB per decade. And it's going to cross the origin at a frequency k0 times 1 over n. So again, if k0 happens to be 1 and your degree n is also 1, then it's going to cross the origin at 1 degree, or 1 radian per second. This is what I didn't mention yesterday, and I don't know why it's not in my notes. I guess again, like I said last time, we don't get this far very often. Yeah?
Can you go over how you get the k naught again? Because I was really confused.
Yeah. So, let's see, our standard form. So we've got, we will have a transfer function that's of the form, say, h of s or h of j omega equals, let's just make this j omega instead. Is going to be, first you're going to have some constant k, and that could be a 1. There's nothing wrong with having a 1 there. And in fact, that's fairly normal for something like a simple filter. If you just I want certain frequencies to get through, and I want other frequencies not to get through, then, and I don't want to necessarily amplify what I'm getting, I just want it to either come through or not, your k value very well might be a 0, or it might be a 1. So you have some constant k, and then of this kind of form where you've got, so ignore that kind of thing. J omega plus some 0 frequency z1. This is going to be one of those poles at the origin that we just talked about, and this is a pole at some other break frequency p1. When we write that in standard form, the standard form of that is going to be h of j omega equals k0 times j omega over z1 plus 1, and j omega over p1 plus 1. And in this case, that value k0 will equal k times z1 over p1. And so if you're kind of trying to go backwards almost, this is one of the things that I also did notice about when I was going on about yesterday, is that sometimes you know, when we're given a form that has this standard form, you already have k0, so you don't have to muck around with k0 or to calculate for it, because whatever constant sitting out here is the constant k0 as opposed to the constant k. But this can be generalized that if you need more k0, if you have more zero terms, you just keep multiplying those in, z2, z3, so on, and dividing by the pole terms, so on. And that will get you your value of k0. Some of the things that we've seen in the past, trying to get this into go back to this form of k, we've been doing some kind of different things and factoring out that like 1 over z1, factoring out the 1 over p1, and that will affect as you're trying to go back from k0 to going to what the original version of k was. But that's the general transformation. You multiply that original constant k times the various zero frequencies and then divide out the various pole frequencies. Good? Okay, so linear terms k, or constant terms k, give you a linear flat line of a magnitude of 20 log k. Zeros at the origin of any degree multiplied by the constant k0 will increase at 20 times n, 20 times the degree, decibels per decade, and it will cross the origin at some frequency 1 over k0 to the 1 over nth power. Poles at the origin of the form k0 over j omega to the nth power will be decreasing at negative 20 times n dB per decade. They will cross the x-axis of frequency at k0 to the 1 over nth power. The last one to kind of look at, or last two to look at, are simple poles of any degree. So if we have 1 over j omega times z to the nth power, and if we have 1 over 1 plus j omega over p to the nth power. And so these are our simple zeros and poles of any degree. Then what they will do is they will, like we mentioned, they will kind of hang out at or near 0 for a long time until it hits that 0 frequency, and then it will increase at 20 times n dB per decade. That's just a mess. So something that's a squared term, for instance, will increase at 40 dB per decade. It will still hang out at or near 0 up until that break frequency z, and then it will shoot up at whatever the appropriate slope is. And similarly, your pole terms, regardless, simple pole terms of any degree, will head along the axis for some period of time, and then will decrease at that same negative 20 times n dB per decade. And that change will occur at the frequency p. So that's kind of the summary of the things that you will see. There are a couple of more situations where you have the complex values, but it's almost not worth worrying about those too much. The final thing is, how do we know kind of where these things start? And from what I can tell, the kind of the generic place that people will start looking at, well, there's going to be two different cases. If you have, one case will be if you have, if there's a pole or a zero at the origin. And that one is the somewhat harder case. So let's skip that one and say, if you do not, if all you have, if there's no poles or zeros at the origin, poles or zeros at the origin. That one works out very nicely with the kinds of things that we saw before, because basically what's going to happen is that it will start out at some magnitude, which is, and it will do whatever it does, but it will originally start out at a magnitude which is 20 log base 10 of k0. And then what it does from there depends on the rest of the transfer function, if you have zeros or poles beginning to affect the frequency response.
Why don't you use K instead of K naught for that one?
Let's see. I don't precisely know the answer to that question, but that the answer seems to be you use K0. So that's kind of the easier one. If you don't have a polar zero at the origin, then it's going to start out, it's going to cross, and this is going to be right near 0 radians per second when it's doing this. When you start seeing poles or zeros near the origin, that's where it starts kind of getting weird, and what you actually frequently see is that people will start drawing their drawing these Bode plots, and instead of this point necessarily being 0 radians per second, they're starting at like 0.1 radians per second or something like that. And what you will do then is evaluate the terms. It's kind of actually a bit of a funny funny evaluation technique, but so you'll take and you'll figure out, so evaluate your transfer function at omega equals 0.1 radians per second. And now that can change if you have break frequencies that are really close to 0.1 radians per second. You might evaluate at 0.01 radians per second. But that's kind of the thing that you're going to do, and you will see that in a lot of the solutions to Bode plots of where they have poles at the origin or zeros at the origin, that it will, the Bode plot x-axis will start at a value like 0.1. So, in the way of a brief example of at least the somewhat harder one, consider a transfer function like, let's see which one I want to do here. Let's do this one. So we've got here h of j omega equals 5 times j omega plus 2 over j omega times j omega plus 10. So there's our transfer function. It's not in its proper standard form, and so figuring out what the k0 term is going to be is is actually going to be determined by well, we have to put it into standard form. But what's kind of nice about this version is that it's very clear to see where the zero and pole frequencies are at. But we do have a pole at the origin, and so when we're figuring out exactly where this is going to start, we're going to use this kind of funny analysis technique. What is very clear about the rest of this particular Bode plot is that there will be a zero at 2 radians per second, there will be a pole at 10 radians per second, and there's already a pole here, so basically you're going to see something that's going to decrease for a while, it'll flatten out between 2 and 10 radians per second, and then it'll begin decreasing again after 10 radians per second. That's the general feel of what's going on here. So, to figure out what is our, we're going to draw this because our first corner frequency isn't until 2. We're going to start this at about 0.1 radians per second. And so our initial value, well, let's call it h sub I, is going to be, we're going to evaluate that at the frequency 0.1. And the way to do that, this works, and I'm not sure that I can give you a good explanation why necessarily. Say 5, apparently this j omega term of j times 0.1 is small enough that we're not going to worry about that compared to the 2 part, and so we're just going to say 2. This one, the 0.1 is significant, so we'll say 0.1. And then again, in this term, the pole, or the j omega part kind of disappears, and so you just have 10. And so the initial value should be, oh, well, so that's part of it. So we have 5 times 2 is 10 divided by 0.1 times 10, which gives you 10. So then the initial value is going to be 20 log base 10 of 10, which I think most of us can figure out in our heads is 20. And so if we're going to start drawing our Bode plot at about 0.1 radians per second, this is going to cross the y-axis at 20 decibels. And because that is coming from this j omega term, it's going to be decreasing from there at the power on this, or the degree of this term is 1, so it's going to be decreasing at negative 20 dB per decade. And now we can kind of go back to this and say, all right, well, this was a simple pole at the or it was a pole at the origin. So if we want to find out where it's going to cross the x-axis, assuming that that's not going to happen, because what can happen is that we can, when we're kind of figuring out the initial slope of what's going on, we can find that based on this k0 term, it might not cross the axis until it's affected by another pole or another zero. So that's the kind of one of the things that we need to look at is when should this cross the x-axis, and it's supposed to cross at k0 to the times, or to the 1 over the nth power. Okay, so we've got k in this case, so we need to find out what k0 is. And k0 is going to be the value of k, 5, times the 0 times, let's see, and then divided by this pole. Are you keeping up with me so far? Okay. Remember our basic form for k, or k0, was we took the original value of k, and you multiply it by all of the various 0 values, and then divide it by the appropriate pole values. So there, what's that?
Like the first, the pole at the 0?
No, because it would be problematic if we put a 0 down here. So we ignore that one in terms of calculating what K0 is. And so that means that K0 is 1. Our general form says that we'll cross the origin or cross the x-axis at K0 to the 1 over nth power. So that's 1 to the 1 over 1th power, or 1. So this is going to cross the x-axis at 1 radian per second. And that does actually get manifested in our Bode plot because the next break frequency isn't until 2 radians per second. Then from there it gets maybe a little bit more straightforward. You got the 2 radians per second that's going to start canceling out the influence of the pole at the origin. It'll flatten out until 10 radians per second, at which point this pole will take over and will start decreasing again at negative 20 dB per decade. Yeah?
Okay, so does that, the first bit there, the first line, does that just start out decreasing at 20 dB per second? Or does it do that the whole time? Because I don't understand how that would work. Because if it was a negative 20 slope, it would cross at 10 radians per second.
Well, I guess here's the thing. Actually, the difference between 0.1 and 1, that's 1 decade. That's the thing to remember. And then the difference between 1 and 10 is going to be a decade. And that's the weirdness of the log plot. Yeah?
So does it start at, like, that we say that it crosses the y-axis at 20 dB, right? Is it at 0.1 that it crosses that, or at 0?
At 0.1.
So there's a gap between, and we just...
Right. And so there's this little chunk of the Bode plot that we don't have. And apparently we've decided we're not worrying about. If you do decide that that's a meaningful frequency, the stuff from 0 up to 1/10 of a radian per second that's meaningful for me, then evaluate this instead of at 0.1 radians per second, evaluate it at 0.01 radians per second. But it seems like, as people have mentioned, and you guys as well as myself, some of this stuff is really not that important because you're just going to pop this into MATLAB or PSpice and get your results out of it. And so, but secondly, this is just kind of a back of the envelope calculation anyways. And so just do the parts that are meaningful to you. Yeah?
Why don't we use the K term for this, for the magnitude?
We do essentially use it because it is, it has influenced what our original value is going to be up here. The K0 term, if we were so let's figure out, we found out that K0 was 1. So what is 20 times the log base 10 of 1? So we did use it, I guess, technically, right? Log base 10 of 1 is 0, times 20 is still 0. And so it didn't really affect what was going on in terms of this original slope.
Earlier it was log base K. Log base 10 K, not K naught.
If I did that with K, then that was a mistake. It should always be done with K0. I hope that I didn't do that because it should always be based on K0. So one more quick example and then let's be done with Bode plots. Here's our last transfer function, which is j omega plus 10 over j omega times j omega plus 5 squared. Okay, so what we have here, we've got a pole at the origin, we have a pole at, or we have a 0 at 10 radians per second, and we have another pole at 5 radians per second. But it's, you can almost call, I think I've heard people refer to this as a double pole because of the squared term here. So in terms of figuring out what's going on with the initial stuff here, it might, let's see, where's, trying to keep up on what I'm doing here. So we would like to first find out essentially where this is going to cross the x-axis or cross the y-axis. So we'll evaluate this at omega naught equals, or omega equals 0.1, and that should be pretty good. So that's going to be 10 on the top, 0.1 here, and 5 here. And I guess what is implicit in all of this is the value of k on this left-hand thing is 1. We just didn't write it, right? So 10 divided by, what's that? Oh, yes, it is. It is squared. Thank you. 0.1 times 25 gives you a total, well, that's not right, divided by 0.1 times 25. That's 4. So 20 times the log of 4 is 12-ish. So our initial value of h, or the initial value as it crosses the line at 0.1 radians, is going to be around 12 decibels. So something less than 20. This, again, back of the envelope, let's not get too crazy about what we're trying to do here. So up here around 12, we're going to start out, we're going to be decreasing at negative 20 dB per decade. And we'd like to figure out approximately where is this going to cross the x-axis. In this case, since our value of k is, I should be careful on that. So we need to find out what our value of k0 is going to be so we can find out where that's going to happen. So our value of k, or calculation for k0, right, is going to be k times, we've got 1, 0, z1, and we've got the one pole, p1. So that's going to be 1 times 10 divided by 25. Because that is still squared. So 1 divided by 25 is 0.04. So that's our k0 term. And what we said even before was that it's going to cross the x-axis at k0 to the 1 over nth power, so that's 0.4 to the 1 over 1. So now, just for kind of example's sake, if you were to have a j omega squared term, that would turn this into 0.4 to the 1 over 2 power or whatever. But we just have to the 1 to the first power here, so the n value is 1. So we're going to cross the x-axis a little bit before 0.5. And then it will just continue decreasing like that until we hit this double pole at 5 radians per second. At which point it will start decreasing at 40 dB per decade because of the squared term. Decreasing or going down at an additional negative 40 dB per decade. And so now it's going to start going down at a pretty steep negative 60 dB per decade because it was already going down at 20 dB here. At 10, that will take away the influence of, it will add a positive 20 to the slope, and so it will just slow down to negative 40 dB per decade. So again, our graph, our Bode plot doesn't start until it starts on the left-hand side of the x-axis at 0.1 radians per second instead of precisely 0. But that seems to be okay. People don't seem to have any problems with that. The original magnitude we solved for by evaluating our transfer function at 0.1. So you have 10 over 0.1 times 5 squared. And so in decibels, 4, that magnitude 4 is 12 dB. It's 20 times log base 10 of 4, approximately 12 decibels. So that gives us where it crosses over there on the left-hand side. We found approximately where it crosses the x-axis. I don't know why I can't say that word. The x-axis by figuring out what our value of K0 was by multiplying through by the various poles and zeros. And then using our formula that crosses the axis at K0 to the 1 over nth power, where n in this case is 1. Of all of the things that I've drawn for Bode plots, this is going to be your biggest friend. Okay, so yeah, we should probably call this K0. I guess I was just copying it off of the notes, and so that should be off of somebody else's diagram. So yeah, that should be K0. But that's, I guess in general, it's probably bad that they used K, because that could be for any constant value. But yeah. This is going to be your biggest friend in terms of dealing with Bode plots. That the magnitude will be flat for any constant terms. For zeros at the origin, it will cross at this particular spot, increasing at 20 times n dB per decade. For poles at the origin, across the x-axis, at this point at negative 20 times n dB per decade. And then our simple poles and our simple zeros are the easiest ones to deal with. And for calculating the initial values, evaluate the transfer function at something close to 0, 0.1 radians per second seems to be pretty reasonable. Evaluate what the magnitude of the function is. Don't forget to find the decibel value by multiplying 20 log 10 of whatever that magnitude is that you solve for. And then you should have a Bode plot. And now, unless any of you have any problems with it, I'm not going to talk about Bode plots anymore, because I am sick of them. But I hope that you at least feel like you understand them. If you don't, please come and ask me some questions, because I spent a lot of time yesterday looking at this to make sure that I would explain it to you in hopefully something that sounded coherent in any way. And if it didn't, I apologize profusely. But so let's see if we, yeah.
One of these?
Yeah, and I think that I will stay away from zeros at the, or poles or zeros at the origin, and just go for, I will give you a very simple Bodie plot. I'm not going to stress you out, and it'll just have the first order terms and stuff like that too. Yeah?
Should we not expect any zeros on the exam either?
On the exam, you might see a polar zero at the origin. And if nothing else, all of the formulas for at least, where it should cross the origin, I'll put those on the formula sheet. So if you need them, they will be there. The one thing that I haven't, one of the things that I haven't done on the exam yet is figured out exactly what the Bodie plot problem is going to look like. All right, so enough of Bodie plots. Let's see if we can do something interesting in the last half an hour with resonant circuits. Okay. So I will draw this just for the sake of the example, but consider just any generic series RLC circuit. It has some current running through its I. There's some voltage across all three of the elements, V1. Then there's a voltage VR across that. There would be a voltage VC across this, voltage VL across this. There's some resistance here, some capacitance here, some inductance here. Simple series RLC circuit. And we've already kind of looked at what the impedance of this is, because we were playing around with this a little bit in our very first transfer function. And that's impedance as a function of j omega is R. And then if we factor out the j, we've got j times omega times L minus 1 over omega c. And one of the problems even on your on the homework that you turned in was, how can we get the voltage and current in phase? And that's basically when omega L equals negative 1 over omega c, well, when they essentially equal each other, when that occurs, or when negative omega L equals negative 1 over omega c, however you want to think about it, the reactive or the complex portion of the circuit, the response disappears. And it's a wholly real resistance, or a wholly real impedance that we see. And that occurs if you solve this and you do it properly. You'll find that that happens at this resonant frequency omega naught, which happens to equal 1 over the square root of LC. And hopefully that looks at least mildly familiar from solving second order circuits. And that's because it's the same darn thing. You're looking at what is called the resonant radiant frequency. And we even called it that, I think, or the natural radiant resonant frequency or something like that when we were looking at second order circuits. And it's the same thing. It's the, yeah. And when this happens, and you have a circuit operating at its resonant radiant frequency, we say that the circuit is in resonance or is resonating at that point. So that is how we start out all of this resonance stuff. Resonance can be a good thing, it can be a bad thing. In terms of musical instruments, for example, you have a resonating chamber of air, or it's a resonating column of air in most wind instruments at least, and that resonance is what makes the instrument sound and sound loud. The longer that chamber of air is, the deeper the sound is and whatnot. With the Tacoma's narrow bridge, as we noted before, resonance was very bad. It shook itself apart. Was there more to it? Probably, but it makes for a good textbook example. With circuits, it's generally a good thing to get the circuit in resonance. We're often looking to try to do that. And it's good because the current at resonance is the maximum possible for the voltage. You don't have any phase differences kind of limiting what the current is able to do. And so what we will define something is the quality factor of the circuit, which can be calculated as shown on the bottom of the slide in a whole bunch of different ways. And they're all equivalent ways, and it's all based on just manipulating the fact that the resonant radiant frequency omega naught is the 1 over the square root of LC. So the most generic version is for I think this is at least for a series resonant circuit. You've got omega naught over times L over R for a series RLC circuit will give you the quality factor of the circuit. 1 over omega naught times CR and 1 over R times the square root of L over C. Those will all give you the quality factor of your circuit. And this is one of those things that is on the formula sheets, and all you really have to kind of do is plug in values to try to figure out exactly what's going on here. So I'm going to write those down myself so I have them kind of handy. Q equals omega naught L over R. It equals 1 over omega naught CR, and it equals 1 over R times the square root of L over C. Okay, so in the way of a quick example, here is a series RLC circuit. .25 millihenry inductor, a 10 microfarad capacitor, a 2 ohm resistor, and a voltage source at 10 at an angle of 0 degrees volts. And what we would like to find is at the resonant frequency, what is the voltage across each of the elements, what is the resonant frequency itself, and what is the value of Q for this circuit. So first, what is omega naught? What is the radiant frequency? 2, what is the voltage across each element? At when it's operating at omega naught, because these have that the impedance of this will change based on what the frequency you're operating is. And then 3, what is Q for this circuit? So let's start out. Omega naught equals 1 over the square root of LC. So that's 1 over the square root of 10 microfarads times 25 millihenries. So 10e negative 6 times 25e negative 3, second square root, second answer. Then flip that, and you should get 2,000 radians per second. So that's the first part. So if the circuit is operating at resonance, then the influences of these two reactive elements essentially cancel each other out, And this is one time where you can say that all of the equivalent impedance seen by this voltage source is just the 2 ohms of resistance. And so what that means is that as we start looking to do part 2 here, that the current does happen to equal 5 at an angle of 0 degrees, which is the 10 at an angle of 0 divided by the 2 ohms, because if we were to plug in and say, well, we're operating at 2,000 radians per second, and I figure out, so what is the impedance on the inductor? It's going to be J something. And what is the impedance on the capacitor going to be? Well, it's going to be negative J something, where the somethings are the same. And so when we calculate the equivalent impedance going around that circuit, crunch it down to one number, all of the reactive stuff, all of the complex stuff is going to go away. So we've got 5 at an angle of 0 amps rolling around the circuit. And if we want to know what the voltage across each one of these elements is, the voltage across the resistor is just, V equals IR. So I times R equals 5 at an angle of 0 times 2. So we've got 10 volts. Well, 10 at an angle of 0 volts. If we go way back a few chapters, we find that the voltage across the inductor is J omega L times I. So we have J times 2,000 times 25 millihenries times 5 at an angle of 0 degrees. So 2,000 times 25 e negative 3 times 5 gets you 250 times J. So it's J 250, or 250 at an angle of 90 degrees. And then the voltage across the capacitor is I divided by J omega C. So that's 5 at an angle of 0 degrees divided by J omega C. So let's take this out and say that's negative J times 5 at an angle of 0 degrees divided by 2,000. And the capacitor was a 10 microfarad capacitor. So 5 divided by 2,000 times 10 e negative 6 is negative J 250, or 250 at an angle of negative 90 degrees. Volts. This one should also be volts. So that was the second part. What you see essentially, if you do the KVL, if you were to do a KVL equation around the loop, you would say, oh well, we've got negative 10 at an angle of 0 plus 10 at an angle of 0 degrees plus 250 at an angle of 90 degrees plus 250 at an angle of negative 90 degrees, and that still equals 0. So everything's okay. It is surprising to think that with a 10 volt source you've got 250 volts at those opposing phase angles. Last thing, quality factor of the circuit. What is Q? Lots of different ways that we can solve for it. The one that I used specifically here was omega naught times L over R, but they're all equivalent, so I'll get you the same answer. That's 2,000 times 25 millihenries divided by the 2 ohms of resistance. That's 25. Plug in the numbers. One of the things that I don't know that I can tell you very easily is, what is the meaning of 25? If you walk up to someone and say, my circuit has a quality of 25. I don't know what that's supposed to mean necessarily. And if someone else comes up and says, well, my circuit's got a quality of 26, I don't know if that's necessarily better or what. But it is something that you can use and walk around with. Here's one trick that you can kind of carry with you. This is one that I don't put on the formula sheets, so it's one for you to bear in mind. The magnitude of the voltage across the inductor will be at an opposite phase, but the magnitude of the inductor voltage will be the same as the magnitude of the capacitor voltage. We noticed that there's 250 here and there's 250 here. They were just 180 degrees out of phase. And that's always going to be equal to the quality factor times the voltage across the source. So our quality factor here was 25. The magnitude of the source voltage was 10, and those were both 250 volts. So this is something that you can kind of carry around with you if you need to do these, if you want to do these a little quicker. Yeah?
I think it's generally safe to assume that the phase is going to be 90 to 90 and the capacitor in the...
That's probably safe. It's been a while since I got into this stuff, so it might... let's see if... Let me double check my notes before I explicitly say that. I think it is safe to say that, at least for series circuits. Okay, here's another quick one. We have a 100 millihenry inductor. We have a source that's putting out 10 in an angle of 0 degrees volts. And we have a 3 ohm resistor. And what we don't know necessarily is what the heck is that capacitor value. And that's essentially what we're going to solve for first. We want to find a value for C such that omega naught equals 1800 radians per second. And once we've done that, so that's number one. Number two, then at resonance, what is Q? And what is the magnitude of the voltage across the capacitor? I guess that should be a question mark. So, first part is just kind of simply working with the formula that we have. We know that omega naught equals 1 over the square root of LC. We have omega naught, it's 1800. We have L, it's 100 millihenries. We want to solve for C. We just start doing the work and hoping that we don't screw it up ever. So, so we have omega naught times the square root of LC equals 1. Let's square both sides to get rid of that root, and so you have omega naught squared times LC equals, well, 1 squared is still 1. That's kind of nice. Then rearrange the terms to get C by itself, and C is going to be equal to 1 over omega naught squared times L. So that's nice. Now we've got the thing that we want to solve for on one side. We've got all the other information that we have on the other side. And so that's 1 over 1800 squared times 100 millihenries. So 1800 squared times 100 e negative 3. And flip that. And we get a fairly small number. That happens to equal 3.09 microfarads. I have the answer for Q based on the same version of the quality formula that I used before, but let's use another one for kind of kicks and giggles here. How about equals 1 over omega naught CR? And hopefully that should give us the same value. So that's 1 over 1800 times 3.09 microfarads. And the other one is the resistor, which is 3. So 1800 times 3.09 e negative 6 times 3. Flip that. Yep. And so that's approximately equal to 60. The answer that I got is 59.93 whatever, but that's the quality for this circuit. You should be able to get that if you plug in the other numbers as well. So we can use our little trick to solve for the magnitude of the voltage across the capacitor. The magnitude of that voltage will equal Q times the magnitude of the source voltage, which is 60 times 10 or 600 volts. Let's see. All right, let's see how much we can get through here. So, if we go back and look at that series RLC circuit, the same one that we drew back here. So here we go. And we were to look at writing an equation that relates this input voltage V1 to the output voltage VR. We would get this particular transfer function, which is up on the PowerPoint slide, 1 over 1 plus JQ omega over omega naught minus omega naught over omega. That's the formula that you end up getting. What that means is, hey, that circuit is a simple bandpass filter. And what that means is that there are frequencies, and usually we're looking for just for a gain of 1 again, but yeah. And so there are some frequencies that it's going to let through. So between some frequency, which we call omega low, and some frequency omega high, those are the frequencies that will be able to get through our bandpass filter. Everything else should be hopefully driven down pretty close to 0 for frequencies that are higher than that. And all of this kind of revolves around omega naught. So omega low and omega high are equidistant from that center point of omega naught in the middle. And so there are a couple of things that we quantify, and these are things that you do not have to remember in any way, shape, or form, because I would not want to have someone tell me, oh, you need to remember one of these formulas walking into the final exam. But the low power frequency, and this is all based on, they call this the half power frequency, where it's actually 1 over the square root of 2 is the kind of the threshold that we're looking for. And so where the gain or the magnitude passes through that point, it does, and that's where omega low and omega high are defined at, is straight across that line. So, and quantifying what those things look like are these formulas here, which basically, if you know what the quality factor is, you just plug it in here, run the formula, and where they came up with this, I have no idea. But this is how you can calculate what the half power frequencies are. That's what, I think I mentioned it, but omega low and omega high are called half power frequencies. And the distance between omega low and omega high is called the bandwidth of the circuit. So that's omega high minus omega low, which is also simply defined as omega naught divided by Q. And that tells you what the the bandwidth of the circuit is. So very quickly, let's at least do, I think we've got one example of doing a bandpass, finding out what the quality or the bandwidth is. Oh boy. All right. So this is kind of going back to our same circuit that we were messing with before, that we just calculated the resonant frequency for. So you can run with that if you want. So we've calculated that at resonance this should be 3.09 microfarads. That's the same 3 ohm resistor. And then 100 millihenry inductor. This is a 10 at angle 0 degree voltage source. And so my claim to you is that this is a bandpass filter, and so we want to find out what are the half power frequencies and what is the bandwidth of the circuit. So we want omega low, we want omega high, and we want the bandwidth. So really it's just a matter of sitting down and plugging in the numbers. So omega low equals omega naught times 1 over negative 2q plus the square root of 1 over 2q squared plus 1. And just as a reminder, we calculated q was equal to 60. And we calculated omega naught was 1800 radians per second. So plug all of that in, and your low frequency should be 1785.06 radians per second. Omega high is almost all of the same stuff. It's just so the difference is it's omega naught, and it's all of this stuff except it's a positive 1 over 2q plus all of this stuff. And that will, when you plug in the numbers, that should take you up to 1815.06 radians per second. And the bandwidth is defined as omega high minus omega low, which is 30 radians per second. Really, this is just an example of putting stuff into a formula. There are existing formulas for calculating this stuff. Take the circuit parameters, drop them into the formulas, and off you go. Let me just, in the last minute and a half here, let me, I've got some examples that we can do tomorrow, but let me go through just the last little bit and tell you there are just some small differences between series resonant circuits and parallel resonant circuits. The slide kind of sums up everything here. Parallel resonant circuits are pretty much the same as the series ones. The only difference is how you calculate Q. The resonance frequency is the same, but Q is now R over omega L times R over omega naught times L, and R omega naught times C. Just use those instead of the other formulas for calculating resonant or for calculating the quality factor. And what we had said in terms of that trick was that the magnitude of the voltage across the capacitor was the same as the magnitude of the current or the voltage across the inductor, and it was multiplying the quality factor times that voltage magnitude. Well, in this case, now it's currents instead of voltages. So I guess if you're interested, tomorrow we can go through some examples of this. So that should give you enough to get through the homework. or at least get started on it. If you have questions, please let me know. Again, tomorrow, what we will do is I will put together a simple Bodie plot question. That will be the first part of the class. We'll do that quiz. Then if you want to, stick around. I will answer as many questions as I can. We won't be on the air, so you can ask all the dumb questions you want, and nobody will have a record of it. And nobody will have a record of my dumb answers either. So we'll see you guys tomorrow. Have a good one.